Ladies and gentlemen, welcome to TechGeek webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is building multi-tenant, configurable, high-quality applications for any cloud. This is the first session of the Technical Architect Workshop being conducted by Techcello. Our guest speakers today are Mr. Janaki Jayachandran, Practice Manager, Cloud, SaaS at Techcello, and Ms. Jyoti Rangarajan, Senior Technical Architect at Techcello. Mr. Janaki is an ardent cloud enthusiast and a prolific speaker at NASSCOM and Cloud Connect event. He has 15 plus years of software development experience and was instrumental in defining the Cello architecture. Janaki enables enterprises and ISVs to define their cloud strategy. Our second speaker, Ms. Jyoti, has 12 plus years of experience in architecting cloud and SaaS solutions for both ISVs and enterprises. She is a chief architect in designing and constructing the Cello product. Jyoti plays consultative role with customers in implementing technical solutions. So without further delay, I introduce you all to our guest speakers. Over to you, Mr. Janaki.
Thank you, Mohini. Once again, thank you everyone for taking the time to be in this session. I am Janaki Raman. I'm going to be covering the first section of today's agenda. So I'll be talking more around the domain and non-domain requirements of a product or application, and how does it help us towards identifying some of the architectural constraints, some of the architectural requirements. So I'll be delving more into that. And followed by that, we'll have Jyoti talk about a couple of NFRs that are very crucial for any product, which would be the scalability and performance itself. So with that, I'll get started with my session. Okay, the domain and non-domain requirements. Now, one of the most common mistakes that people do is in segregating the requirements of a product or application. Let's try to break up the requirements into various segments, and let's try to analyze it taking HR management and banking management system as examples. So here we have classified under 4 categories. Let's take the first one, the domain requirements. So what are these? These are going to be the core requirements of any given software. For example, in case of an employee management screen being a critical one for HR management solution, and likewise the customer management functionality is going to be critical for a banking system, right? So these domain requirements are going to be the DNA of that particular product. It's going to be, of course, unique across the products, and in some cases it might overlap as well. But by and large, it's going to be very specific to the domain as well as the product. For the adjoining requirements, these are those features that help in governing the core features itself. So these features may not result in the addressing the core business problem, which is what addressed in the domain requirements, but then these are going to be the ancillary features which could help in governing and managing these domain requirements. A good example could be the user management and role-based access control features. So these features, if you look at, are applicable for both HR management as well as a banking system. Right. So in case of HR management, it could be who sees what information, who can look at an employee's salary data, for example. So how do you control that access of it? So you need this functionality to be able to determine who can operate on which data and view which data. Similarly, on the banking side also, you want to have different levels of control, in fact granular level also, so that you can determine what a clerk can do, what an executive can do, what a manager can do, what kind of transactions they can operate on, right? So the adjoining requirements is going to be the surrounding requirements helping you to govern. But the only additional consideration here is the adjoining requirements may vary from case to case. So in this example, we have the banking system, in addition to the role-based access control and user management, may require, say, an adultery detection kind of a feature, which can avoid improper usage of the system, or someone trying to do something weird on the system. So you should be able to detect it. So that becomes an adjoining requirement in this case. The runtime quality requirements. These requirements define the expectations of the software while it's in live or in production. For example, the concurrency of users, the system's response time during various load stages. Now, these are the requirements that are common in nature, and as you could see between the HR system and the banking system, there are a lot of similarities in terms of the runtime quality requirements. Now, while they remain common, the extent to which you want to support these requirements will vary from system to system. For example, if you take the concurrency itself, the HR system, it may be okay to have a concurrency support of, say, 300 users, compared to the banking system where the concurrency may have to be as much as 5,000 concurrency and 5,000 users being able to concurrently access the system. Right? So in general, the nature of these requirements remain the same, but the degree to which you want to support can vary from product to product. And the last segment is the software management part of it, software management requirements. And these are similar to the earlier one, except that these features are related to the maintenance of the software on a long run. Right? And once again, the attributes and nature of these requirements are similar to the previous one, what we saw. Let's try to take a look at the effort distribution of these requirements. So this slide throws insight on the distribution of the effort involved in a typical project. So when you say typical project, we are talking about a project of an average size, right? And we are trying to see the effort involved against accomplishing the various segments of requirements which we saw on the earlier slide. So as we can see, the core requirement of a typical sized product or an application is only 40% compared to the rest of the requirements. So the remaining 60% comes from the non-core requirements, or what we call the non-domain requirements. So if you look at this, gives a specific insight on where your focus should be. Now what happens, like I said initially, one of the common mistakes people do is to mix up these requirements and trying to address all of that at the same time, right? And more importantly, some of these requirements cannot be addressed at a later stage in the project. Let's take the next slide, which will give some information on that. So these are the various non-domain requirements, and by implementation across the phases, if you look at, so we have around the architecture phase constituting around 35% for addressing this particular requirements. And then we have the solution design taking almost 45%, and the coding alone contributes only 15%, and the QA and the QC, a part of it, taking up the remaining 20%. So the predominant of the effort goes towards addressing these non-domain requirements are coming from the architecture and the solution design, which is where you kind of form the high-level design or the framework or the technical approach towards addressing the non-domain requirements. Now what happens when people try to mix up these things, it all goes as requirements, and then people try to solve these requirements as part of the regular functionality, which could be an employee management screen or a banking management screen, which means your developers are going to be ending up taking up these non-domain requirements and trying to address it as part of the regular requirements. So which is a major mismatch, because these non-domain requirements cannot be addressed in a coding phase. It can only be addressed at an architecture or a design phase, and cannot be addressed by a developer, but rather by an architect kind of a person. So why should I handle these non-domain requirements? What if I just skip them? What kind of problems one might encounter. So some of the key risks involved in skipping these non-domain requirements starts with the data loss. The data loss could be a result of so many attributes, including incomplete transactions, inadequate backup policies in place. One of the examples I'd like to mention here was there is this school management software which has been used across the schools, and one of the schools was conducting an examination, and it happened to be that an examination happened at the same time. So the entire school district was taking up an examination, and during the examination, one of the kids' answers were totally lost. For some reason, the system did not save those answers. And that kid happened to be, unfortunately, the kid of a mayor. And this was a real incident, right? So it was a kid of a mayor, and you can understand the amount of pressure the company would have gone through in resolving it. And what they had to do was to kind of spend almost 2 months, and they had to deploy their entire QA team, their engineering team on site, trying to replicate the problem, because it happens only under a certain load, under a certain concurrency. So replicating it was not that easier. So they had to spend a lot of money, a lot of time, a lot of pressure to even find out what the problem is. End of the day, it was a small mistake done at a coding level, but then it took a lot of time for them to address it and overcome that risk. Other risks include the security breaches. There are a lot of security compliances that have to be made, and some systems require high level of security, like banking and financial related applications. So the degree of it again varies. And when you go for web inherently brings in a set of web security threats, which again have to be handled. And of course, not handling these things are going to end up with unhappy end customers, which in turn could result in business loss or customers attrition. Right? Application outage could be another major risk, a threat. Again, if you look at the type of applications, there are applications which do not even provide you the time frame to do an upgrade. An example could be an application that is dealing with long-term healthcare. This is an application, a product that is used by long-term healthcare centers. And long-term healthcare by name refers to those healthcare centers where very old people are being maintained and treated for ailments, right? So what happens is this particular product is being used by the nurses to provide medication to these old people. And these old people go through medication every 2 hours, every 3 hours, depending on the patient, depending on their ailment. There is a lot of medication that happens through. And what happens is this happens across the clock. So because medication can happen at any time for any patient. So you literally don't have any time to even do an upgrade or a standard maintenance effort on the product or application. So this poses a different level of challenge. So you can assume what happens when you don't consider this. An application is out for 2-3 hours, then we are talking about some serious fatal outcome as well, because you are not going to be treating those patients who could be under very severe ailment as well. So those are some of the cases that you will have to consider. These are very high critical, high sensitive things, but there is also this risks which are long term in nature. One of the best examples is the maintenance risk that could come along. Many times, considering the time pressure, considering the various priorities that are there, people tend to take shortcuts. Shortcuts work, but they don't work on a long-term basis. So you might address the, for example, the concurrency problem of say 200, 300 by quickly writing some queries or writing some kind of logic and maybe upgrade the hardware. You may be solving the problem today, but down the line, the application or the software may not be able to scale up. And hence you might even end up going through a complete re-architecture of it. So either that, or you either end up in spending a lot of time in maintaining the product. In either case, from a long-term perspective, it's going to be a killer. You'll be spending a lot of time, and operational expenses are going to be very high in maintaining such softwares. And the more product is rigid, the application is rigid, the slower you're going to respond to market. And we know in today's market, responding back as soon as possible is going to determine your success in many instances. So your product should have the agility, should have the kind of configurability that can help you respond in a much quicker time frame. Now, failing to which your competitors are going to be addressing it and they are going to be taking an edge compared to your product. And once again, compliance breaches could also lead to serious troubles. And again, not all products require this, but then the degree of it absolutely varies, and you need to determine what degree your product is going to be supporting. So we looked at the various segments of these requirements, but what do we conclude out of it? So let's try to understand what is the overlapping nature between these requirements. As I said, the domain requirement, there is not much of overlapping unless we talk about two products within the same business space or same addressing the same business problem. But otherwise, it's going to be completely different. But if you take the adjoining requirements, which is where you have this user management, security control, access control, and so on, now that could by and large remain as much as 60% same across the products. We are talking about different types of products. We are talking about a employee management, a banking solution, a school management. Regardless of this, the adjoining requirements could be common as much as 60%. Now only the 40% could vary or could extend depending on the type of product we are dealing with. Now this percentage is even higher when you talk about the solution runtime quality requirements and the software maintenance requirements. Now in these two cases, it's as much as 80%. So we are talking about runtime quality requirements like the concurrency, the performance, the response time, and so on. So these things are almost common across all the systems. And as I said, the degree alone may vary. Depending on that, you may have to tweak your solution. But by and large, they remain the same. So these various segments of requirements is where the architecture comes into picture, is where the architecture phase itself is going to try to address in a product or application. So the commonalities between these various segments can very well be summarized into what we call as NFRs. NFR standing for the non-functional requirements. There are as much as like 24 NFRs that could be applicable to a product, but not every product has to be supporting all those NFRs. It purely depends on the type of product we are dealing with, the kind of business case we are trying to solve, and the kind of domain solution being provided. So depending on these scenarios, you might have to pick up the right NFRs that are required and also determine the goals for these NFRs. The goals itself could be, for example, when we talk about product customization. Customization is the capability to kind of customize your product according to the end customer's need. Now, the use case here could be, for example, you want the customers to be able to add additional fields to existing screens, and they should be able to capture this additional information, right? Now, you could either take it as an implementation. In a traditional model, we take it as an implementation requirement. We have the developers code it and then modify the code, bring this additional field. But then if you talk about SaaS or multi-tenant kind of scenarios, it becomes even more critical for allowing the users to be able to specify this additional field information, and more and better, we give the control back to the customers to do it by themselves, so that they need not even come back to the support teams for implementing this customization. So scalability is one such kind of a thing, the performance of the system. These are some of the common trends or common NFRs that are applicable for most of the products. So there are some NFRs which could be not so very critical. For example, something related to your deployment model, or it could be related to your modifiability. So there are so many NFRs around there, but they may not be as important as some of the other NFRs we saw earlier. So for the rest of this session as well as the next two sessions, we are going to be picking up some of these important non-functional requirements, and we are going to try to understand their impact on the architecture, on the product, and how do you address these NFRs, some of the best practices involved in addressing them, and how do you typically approach it. So those are the kind of insights we are going to look into the rest of the session as well as the next two sessions. So with that, I'm going to hand it over to Jyoti, where she'll be covering two NFRs today, which will be the scalability and the performance. Over to you, Jyoti.
Thanks a lot, Janaki. So like Janaki mentioned, there are a lot of non-functional requirements that are key to the success of the product, right? The functionalities could work very well, but then if the underlying quality of the system is not good, then it's not going to meet at the end of the day the requirements of your user. Say for instance, the functionality works well, but then when 2 or 3 people even log in, then it fails, or the response time of the system is very slow. The entire user experience goes for a toss, and no matter how much effort we put in building these functionalities, the end goal is not met, right? So that's the importance of the non-functional requirements in any application. And 2 very common important non-functional requirements are scalability and performance. So what is scalability? It's the ability of the system to respond to higher load. What could a higher load mean? It could be either an increase in user concurrency. Today, maybe the system supports 500 users, but later on, there could be a requirement to support 5,000 users. So the way your system is working today or functioning today with 500 users, you should be able to take the same system and make it work for 5,000 users without having to change your application at any level. So that's what is called scalability. Now, it's just not user concurrency. It could be the load of volume that is being transactions. Say for a payroll system, you could be maybe working with 1,000 records today, and later on you should be able to process 1 million record or so. So there the data volume that's processed could become higher. So as a whole, the load that is being handled by the system, be it concurrency, be it the volume of transaction, be it the network bandwidth that the application experiences, if it grows exponentially, the application should be able to handle it with grace. So that's what is scalability. Now, what applications need scalability? Now, not every single application that's written for every enterprise needs to go through this rigorous exercise of scalability, but there are few kinds of products or applications where scalability becomes extremely important. And to name a few are SaaS multi-tenant applications. If you take SaaS-based applications, which are applications that are centrally hosted and being served to the clients via network, and especially as a deployment model, if it is multi-tenant in nature, we'll see more about what multi-tenancy itself is. But to explain in very short term, it's the ability of the system, single instance, to serve multiple customers. Say they would, you could take an example as Salesforce. So there is one instance that is deployed, but then it has to serve many customers with it. So each customer might have varying degree of users with it. So the ability of those systems to grow is very high. The volume that is expected in a SaaS multi-tenant system is very high, and hence scalability becomes one of the most important NFRs for those applications to handle. The other kind of applications are obviously the growing enterprise applications. If the enterprise is in a vigorous growing mode, then the number of users is expected to grow also exponentially, and hence those systems need to scale rapidly. The other kind of applications are applications with periodic bus. For example, there could be travel sites where which is running a promotional activity, right? So when there is a promotional activity, the number of users expected on the site is extremely high, right? So during those short periodic bursts, the application should be able to scale rapidly. And similarly, any consumer-facing internet applications like banking or e-commerce applications again need to scale rapidly. So these are the kinds of applications where scalability becomes one of the most important non-functional requirement for growth. So what are the general approaches for scaling? So there are two obvious approaches. One is scale up. Scale up is very easy to handle. This is simply adding on resources. So you have a specific memory, specific CPU power, specific bandwidth today. You increase those and hence handle more volume, right? So that's scale up. So every application, the first target is to increase these because it's pretty easy from development standpoint to do that, because you don't have to really invest on changing your application code or architecture or design. So the first cut you would do is to go and increase the resources to be able to handle more volume. The bottleneck with scale up is no matter what, how much ever resources you add, there is going to be a rooftop when you reach. Beyond that, you wouldn't be able to scale up. So what happens after that? That's a reason that every application needs to be able to scale out. Now, scale out is a technique wherein you add more nodes to the system and then balance out the load to the nodes, and hence increase the load that is being processed. Right? If you look at the second diagram, you're adding more nodes. So today, maybe there are 2 servers processing 500 requests, and later when you increase, say, like 20,000, you just add on more servers to it and make it process more load. So that is what scale out is about. So it's very important that on a long term, your application or a product is able to be scaled out and just not be able to be scaled up. So let's take any application. So what are the layers or tiers that any application or a product would have? It generally has a presentation layer, which is responsible for the rendering of UI. It could either be a web or a TIC client. The second layer is obviously the business logic layer or the application layer. This is where the business processing or the business functionality runs. The data storage layer, which typically takes care of all your data access, manipulation logic. Now, we look into each of the layers and discuss the best practices and patterns on scaling out each of them. Web and business layer scalability, it's almost the same. You have either a web server or an application server which is running the presentation tier or the business logic functionality. The one obvious way to scale it is by scaling up, which is adding more resources to it. Now, the way you scale out is typically by adding a load balancer in front of the web server or the application server. Now, thankfully, most of the web servers or application servers inherently support load balancing mechanisms, and hence it could either be a software load balancer or a hardware load balancer. You add the web server nodes or the application server nodes to a farm and then have a load balancer before that, and then the load is automatically distributed. So with the current technologies, achieving this is very easy, and especially when you are your application is either based on Java or .NET or Ruby on Rails. Even from an application coding perspective, being able to scale out and web layer or an application layer is going to be extremely easy. But apart from that, there are few design level considerations that one should take so that your web and application layer is able to be scaled out, right? So what are they? The application should have a centralized out-of-process session usage. What happens is there are different nodes in the system, right? Like web server 1 and web server 2 are going to be serving the request. So if the session is in memory, the session that's available for web server 1 is not going to be available for web server 2. So hence, the problem is you lose the session and then the application starts behaving differently. Hence, in a load balance environment, you need to go for an out of process session or a centralized session. So most of the technology supports either a database driven session or a completely separate state server for maintaining session. So you should adopt to one of these in a scaled out scenario or a load balance scenario. And same is the case with the cache usage. From a cache, again, if you go for an in-memory cache, the cache that you're using for web server 1 or an application server 1 is not going to be available to a web server 2 or application server 2, and hence you're going to miss out data. So what you need to do is to go for techniques like distributed caching or say a centralized cache store that all your web server or application server talks to. So this is one thing that a lot of applications do not handle, and hence once they scale out, they realize that caching becomes a problem. So session and cache are very, very important to manage, and the way it is architected is very important in scaling it out later. Apart from the centralized session and cache, some of the principles that you can follow to scale out a web layer or an application layer are asynchronous request processing. So when a request comes in, you could spin off another thread or an asynchronous thread to process it, so that the main thread is released to handle more load. So this is one pattern that you could use to be able to handle more load. And even when the number of sessions that is expected is extremely high, right? Sometimes even no matter how many ever web servers we add, we wouldn't be able to handle such a kind of load. So what you could do is to go in for a queue-based processing, where you collect the request, queue it, and then asynchronously process and return back to the user. So that's something that you could follow as a pattern when you are expecting very high number of load and you do not want to lose out those requests. So this is something that you could use. So in process parallelism, again you could go for multi-threading concepts to spin up the request processing itself, so that your capacity of the servers are there to fulfill more requests. Stateless design, when it comes to an application server, always follow a stateless design so that every single service or every single web service is able to be scaled out individually. Right? Because that's very important when it comes to the application layer scalability. So these are, whatever we saw now, are some of the essential things that you need to do, or some patterns that you could follow to increase the scalability on the web layer or the application layer. Now, moving on to the database scalability. Web and application level scalability is actually easy. The most difficult portion to scale out in any application is the database. The inherent nature of the database dealing with storage, right? Its state becomes very important, hence it's very difficult to scale out a database. Now, what are some of the choices you have? The first choice you might have to take architecturally is whether you need to go for a SQL based storage or a NoSQL based storage. So what is a NoSQL based storage? It's not a relational DBMS. It's a flat storage could be stored as either a key value or just an object store, or it could be a graphical node storage. It does not deal with the typical RDBMS concepts like be it referential integrity or and so on. So what it ensures is though extreme scalability. Since you're dealing with some data that it has to store and retrieve back, it is capable of handling a very large load or volume. So that's the advantage that you get if you move to a NoSQL database. But then not every kind of application can benefit from a NoSQL database, and it's very difficult to write all the application based on this as well. So when do I go for a SQL and when do I choose a NoSQL is a common question. So if you have different kinds of data, right, you have different kinds of entities in system that are related. A typical line of business application, if you take, would have such a need, right? There are going to be hundreds and 200s of tables which are completely different in nature, right? If you are going to handle such an application with NoSQL as the backend, you're going to write a lot of code to do that, right? So that is when a SQL DB makes a lot of sense. So number one, you have a lot of non-related data that you will have to store. Second, the search and reporting of the data becomes necessary. So in such cases, it is very easy, or it makes a lot of sense to go for a SQL-based database, right? And again, you need to make a call, like not all applications need very high volume, right? Even RDBMS are capable of supporting a huge volume. So you need to look at the capacity throughput of these RDBMS, and beyond that if you need scalability. For example, if you take applications like Facebook, right, a typical RDBMS wouldn't be able to serve such a high volume, right? So, and the kind of data if you look at it, it's going to be not too very relational in nature, but it's rather same kind of data that you're going to store, but the volume is going to be very high. And there, it makes a lot of sense to go for a NoSQL approach compared to say, employee management system, where it's completely dealing with the relations between the employee and the different departments, designations, and so on. So in those cases, it's better to go for a SQL based approach. So NoSQL, you have, when do we go for it? When you have similar kind of data, and then it's more on a volatile. When you have a lot of volatile data, again, preference for a NoSQL should be higher. Now, it's not mandatory that you choose either SQL or a NoSQL database for an entire application. Most of the applications, in fact, work with both of these as hybrid. For certain scenarios, the application could choose and use a SQL DB, and then for certain scenarios, it could go for a NoSQL. So, a hybrid mode is a very common pattern that applications use in order to scale out the data. Now, within a SQL-based RDBMS, right? Within an RDBMS, what are the options available to scale out? Now, one common way to scale it out is using a technique like we saw for web server or an application server, which is load balancing. Some of the RDBMS provide this facility. Like for example, Oracle has an Oracle RAC which allows you to load balance the loads between different Oracle nodes. But unfortunately, this is not available in a lot of RDBMS. Even the popular RDBMS like SQL Server MS SQL does not have it. So the advantage of going for an inherent load balanced RDBMS is it's extremely easy from a development perspective. You don't have to really take care of the pain of load balancing at your development, be it architecture, be it design, be it coding. It's more handled at the hardware level. But then it's very expensive and it's not too very easy to implement and maintain. So those are the disadvantages of going with that. So what is the other mechanism that if you don't have the capacity or capability to load balance in the RDBMS that you choose, and you don't really want to shell out a lot of money, so what is it that you can use to scale out your database? You would be able to do it using a principle called sharding. So sharding is splitting your load or the data in a table horizontally, that is by rows. So if you have millions of records, what you could do is you could split it to multiple servers. Say first X number of rows is in server 1, the next X number of rows is in server 2, and so on. So what happens is the load, you are writing an algorithm to split the load to 3 different servers or 4 different servers. Alright. So it's important to find the proper partitioning technique in order to do that. So you should have some logical separation within your row itself. For example, in a SaaS-based multi-tenant system, the tenant ID or the tenant identifier could be a very easy partitioning key to be able to separate out the load. Right? It's important because the rows within one shard should be able to be quite close enough so that all the requests mostly go either to server 1 or server 2 or server 3. Otherwise, if all your requests is going to span all the 3 databases, the load is actually not going to be balanced. So hence, it's extremely important that you rightly choose what you're going to partition with and what is the key based on which you're going to shard. Now, what are the cons of going with it? You obviously need some development effort in order to build such sharding and implementing in your application. So if you have to implement in your application, you need to actually do some kind of design level changes or implementation level changes in order to achieve it. But the advantages it is completely under your control. You would be able to manage it, and it is also cost effective. Some of the consideration for sharding: the sharding key needs to be determined carefully. You could use a read-only database for reports and shard only the transactional data, so that way you would be able to very easily split the load for read-only, and only for transactional data you could go for technique of sharding. So you need to actually have a lot of implementation considerations as well. For example, between 2 shards, you cannot actually query the data. You wouldn't be able to reference 2 shards in your query. Certain RDBMS like MS SQL provides you techniques like distributed views, partition distributed views, which gives you a integrated view of all the shards. So you could use such techniques to make your development faster when you go for shards. Similarly, in some data stores like SQL Azure, there are federation services available that completely abstract the concepts of shards, and the development is also quite easier with that. So you could either look at the capability of such service, which in order to fasten your development and then also be able to scale out your database. Shards, use it only when it is necessary, because otherwise it could prove to be a performance overhead. And also when you want to rebalance your shards, for example, now today you have on server 1 50,000 records, and server 2 you want to move some of the records to server 2. You should follow some design principles like the choice of the primary key, etc. should be properly analyzed if when you want to rebalance the rows between the shards. So these are some of the considerations that one has to take when you choose to shard the database. So as a summary, what are the ways to scale out? The first choice is you either have you either can go for a NoSQL based database or a SQL based database. So based on your application need, you need to choose one, or you could even go for a hybrid based on the requirement. Within your RDBMS, you would be able to scale out either using the principle of load balancing as available in few RDBMS like Oracle RAC is what helps you in load balancing, or within the other sectors of RDBMS like MS SQL, MySQL and so on, you could use the principle like Sharding, right? So this is how generally you would be able to scale out the database layer. Now we looked into how you would be scaling out a web layer, an application layer, and also a database layer. Now there's one more layer that people do not give enough attention for, which is backend processing or a batch processing component, right? So there are obviously a lot of components that are going to be a lot of batch jobs that needs to be run in every application, right? So when the latency of those jobs being processed is a problem, you should definitely look out scaling out that layer also, be it a Windows service or a command prompt service, which is processing these jobs, needs to be able to scale out also. So today if it's going to handle a job of, let's say, 10,000 records, it should be able to be scaled out to say 50,000 records by easily scaling out, right? So the important patterns that you could follow is again a queue-based processing. So all the requests asynchronously can come and sit in a queue, and you could have your load balancing algorithm to split the jobs itself to different servers, and the service could just pick it up and then start processing. So this is one important way by which you would be able to scale out. You can see that you have different units talking via a queue, and the request just rise to a queue, and then the units pick it up, processes it, and presents back the feedback so that it's available for the response of the job. So this is something that you could use to scale out your back-end jobs processing as well. So what you're seeing now is a typical deployment diagram of an application. As you can see, you have a load balancer. Behind that is your web server farm. You have a cache server farm. There is also mentioning about distributed caching. So it becomes extremely important to be able to increase your memory of your cache as well, right? So hence it's advisable to go for a cache server farm. Again, you have a lot of caching technologies like Windows App Fabric or Memcache, which very easily would allow you to do that. You don't have to write your own caching technology. And again, application layer is load balanced. And you could also see that the database is being sharded. So that's one thing that you can do. You could shard your database to have multiple servers to handle the load. So as you can see, every single layer in your application can be scaled out, and it's advisable to scale out these so that each of these layers individually is able to handle huge volume. So how would we able to leverage cloud for scalability? So cloud is a very attractive option when you have a scale up and scale down requirement, especially for cloud burst scenarios, right? So we also talked about a scenario where there are periodic bursts. What happens is in some period of it could be either some hours of a day, or it could be either some days of a month, or some months of a year, you would need a high scalability, but rest of the time the application does not demand that much of volume. So in such cases, what you should be able to do is very quickly ramp up and ramp down. So in such cases, cloud becomes a very attractive option. You could use the auto scale out and scale down technique either for a storage or compute to be able to do that. You could also use the data services offered like a simple DB from Amazon, or the Windows Azure storage from Azure to be able to use a NoSQL kind of approach to be able to scale your data. You could even use caching services available from a cloud. You have Azure caching services from Microsoft. You have Amazon Elastic caching available to you. So you could use those as well from cloud. So when you have a very high compute need for an operation, you could either look at cloud, or as discussed, when there is a periodic burst of volume, you could look at cloud. So that's on the scalability. Let's move on to performance. Performance is the measure of response of a system. So you send a request, when do you get the response back? So and how many requests are being able to be processed by your server, which is the throughput. So both of these constitute the performance of your system. So when we talk about performance, what are the phases in which you have to handle performance? Performance is not just a single phased exercise. So you need to watch and carefully monitor and manage performance at every single phase of the project, right? Right from architecture till your QC and deployment, you need to be watchful of the performance. So in what phases, what should I concentrate on? Typically in an architecture phase, the first thing that can totally make or break a performance are the technology choices, right? That we discussed whether we have to go for a NoSQL or a SQL database. This is one very important decision that you need to make, right? So if the technology itself is chosen wrong, there's no way you could give a better performance. Simple things like whether I need to have a web service or not, whether I have to go for a SOAP service or a REST-based service, what kind of third-party system should I use. So those all are very critical for determining the performance of an application. From a high-level design, again, things like the design of parallelly running a process, asynchronously running a process. If you have a lot of records to be inserted, using techniques like batch and not again and again hitting the DB, these all can improve performance. So these are the aspects you should look for in a high-level design of a system. In a low-level design, you need to ensure that the resources are not highly utilized. So the calls that you make at every single procedure or method needs to ensure that the resource usage is optimally minimized, and you should also look at ways to use caching and the right strategy for caching to be able to improve the performance. From a coding, what could impact? Obviously, bad queries. The queries that have a lot of joins, unused logic, looping, so resource consumption within looping. One common mistake or one common pitfall on performance that we have noticed is if there is a huge loop, like say 1,000 records that is getting looped, and within the loop if the code is written to hit the DB, obviously the performance is going to be pretty much hit there. So such places have to be carefully watched for from a coding implementation per se. From a deployment, proper capacity planning is required to ensure performance. So every single system needs its own capacity, right? So you need to properly test and come up with the capacity of your system and ensure the right hardware and are in place to support your system. So that's something that's important. That's an important exercise that you need to do for deployment. And for network transfers and integration impacts, whenever you have a web service or whenever you're talking to some other system out of the process, you need to ensure that the calls are not chatty and you minimize as much network calls as possible to be able to improve performance. So as a practice, what you need to do is design for performance, develop for it, measure it. This is one thing very critical. After you code, use code profilers, profilers that could profilers for your queries, profiler for code, so that you ensure performance at a certain level. Then again, you could use testing tools like the load runner or JMeter to performance test it. And once you do that, you should have a tuning phase to correct it. So some performance are easy to achieve, right? The moment you follow normal design techniques and coding techniques, it's easier to achieve. Some needs denormalization, right? You need to flatten out either your database. You need to go against the principles of object-oriented programming to be able to achieve performance. So in those cases, you need to look for ways to denormalize and also tune. So this is an important exercise that any application should take in order to ensure optimal performance for the load. Now, what are the mandatory candidates for performance testing and tuning? Wherever you have very high volume, wherever you're dealing with algorithms, or if you're dealing with a real-time system, for example, stock exchange kind of systems where latency is totally not acceptable. So such systems need to definitely go through a complete performance engineering and benchmarking exercise. So these are some of the best practices for performance. From caching, you need to cache wisely. Use small objects for caching, especially because it's going to be out of memory. Watch out for costly operations within a loop. Could be DB calls that you're making within a loop. Avoid such DB calls within a loop. Acquire late, release early. Be it transactions or opening a connection, do it only when you need it, and moment you finish using it, immediately release it back. Use asynchronous patterns wherever possible. Use parallelism wherever possible. Code for concurrency. You should always code for concurrency. So keep in mind the logs when you are coding for multiple DB calls. And it's a common myth that I have to fetch the entire DB at a once so that I should not go back to the DB at all for later queries. It's a very bad practice. So maybe 3 simpler DB calls is much better than one huge query with multiple joins. So you need to carefully watch out for a query with multiple joins and avoid it. Minimize the query set at the DB. Keep transactions slimmer. Use caching effectively. For the network calls, you go for less chatty calls. Distribute your processing to application layer and don't overburden the DB. This is one very common mistake people do. DB is for data storage. So the moment you start writing a lot of business logic, the processing of it is going to be utilized only for the business logic functionality. So, and it's not very easy to scale that layer also. We just saw it. So hence, move your business logic to your application and let the DB handle only the data manipulation part. We use batch processing wherever huge volumes of records are processed. Profile the code, tune it, and in case you have a very huge page size, you could use techniques like compression and so on. So these are some of the engineering best practices that you could follow to improve performance. With that, we come to the end of this particular session. I hand it over to Janaki.
Thank you, Jyoti. So I think you can feel free to post your questions, and we'll try to answer as many as we can. So we'll start taking up the questions. Okay, we have a question here. So we have a question from Lakshman Reddy, and his question is there any way to increase or decrease my hardware cost according to the number of users accessing my servers, and without using any pass? It's definitely possible, Lakshman, and you don't need to have a pass in place to achieve this. Today, as Jyoti was mentioning, cloud computing has opened up a lot of opportunities where you can consume a wide range of resources, including hardware, computing, storage, and so on an on-demand basis, on an on-need basis. So what it means is, say one of the periods you need to support a lot of users, a lot of transactions, you can take additional computing power from any of the cloud computing providers, and you can just use it only for the period and then release it back to them. So you don't necessarily need to have a pass to accomplish this. You could accomplish this using any of the cloud providers, including IaaS and other categories. So we have another question from Chandra Shekhar. If both SQL and NoSQL is used, then what are the best practices to decide what goes where and how is that managed without additional overheads? So I will have Jyoti answer this one.
Yeah. So like I mentioned, any data that is more relational needs to, the first target of you should be to look at the RDBMS. And there are lots of applications like metadata or it could be like just the attribute store or whatever that needs just a key value storage. So you don't need a lot of referential integrity there. You don't really need a lot of transactions going on there. So for that, you could go for a NoSQL database. So could you please tell again what is the difference between scale up and scale out?
In addition to that, we have another question also from one of that person. So they wanted to know about the difference between scalability and elasticity. So maybe you can combine both these and then answer it.
Yeah. So scalability, see, scale up is a technique wherein you add more resources to your hardware, right? Today I have 4 GB RAM. Now you add 8 GB RAM to it and make it perform better. So that is, it could be like that. Today you have a dual core, make it a quad core or 16 core processors, and that is what is called scale up. Scale out is where you would be able to add more nodes for the processing to balance out the load. So today I have 1 server. Tomorrow I would have 2 servers, 3 servers. So it's, you're adding more boxes itself to distribute the load. So that is scale out. Okay, and elasticity is capability to scale up and scale down very easily. For example, today I should be able to ramp up very easily suddenly to a 4 service, and then when I don't need it, I just should be able to come back to 2. So that's the elasticity, and that's what is usually provided by the cloud environments. Could you please explain multi-tenancy? I think we have a separate topic for multi-tenancy in the next session. I think that would be very useful to answer this question.
Just to briefly touch upon, it's basically an architectural pattern that can be adopted to make your software work differently for different groups of people. So basically, the requirements could vary from one group to another group. The group could be customer or department or any logical group. But then how do you make the same code to work differently for different groups? So that it's an architectural pattern. We'll look into more, as Jyoti mentioned, during the next session.
How is the sharding available in Azure, etc., different from the partitioning available with Oracle? See, in Azure, so Azure has something called federation services. Again, sharding is actually an architectural principle, right? It's a design principle. So with Azure as well, if you go for SQL Azure, you would be able to shard your database, but they have something called an Azure Federation service which sits on top of it and automatically manages the shard. Now, Oracle load balancing as the technique, it's not sharding. The data doesn't necessarily need to be sharded or split to multiple servers in order for Oracle RAC. So that's the primary difference. So sharding could be done in MS SQL, in MySQL, but SQL Azure kind of RDBMS has extra provisioning to abstract that layer out. There are lots of questions on sharding. So again, I think the questions are around how does it affect performance and so on. So yes, you would see it's all, you need to weigh it like this, right? So performance and scaling. So both are interconnected, but if you want to introduce principles in order to scale out, you're going to lose performance to a certain degree. But then you would be able to achieve it using techniques like caching, or the application layer could be smart enough to shard the right kind of data and pick the right kind of data from the right server. So you could employ such techniques in order to get away from the performance overhead of sharding as well. But then from like if you are just looking at say 500 records I want to fetch, if you go for sharding for such records, it's going to be an extreme waste. So that's why I also mentioned you should have to look at when you have to shard. Don't shard from day one where you don't have records. When you really need a complete scale out and when you're sure that your database is not able to handle that volume, that is when you should have to start sharding your data, right? But then if you want to do it at a later point of time, you need to design for it earlier and then implement for it earlier. How do you achieve referential integrity in sharding? With enough shard, you would be able to achieve referential integrity, but then it's recommended not to use it a lot because you could move out one portion of the data elsewhere. But if your the data within a shard is logically complete, right? So like a multi-tenant application where most of the data are going to be related only within a particular shard, you could still go ahead and use referential integrity in those cases. But if you're talking about a social networking site where the different data could lie anywhere within the system, their referential integrity should be handled at an application layer. Okay. So application performance seems to be dependent a lot on the transport between the server and the client. For example, just by changing the transport both from XML to JSON, you gain a lot in app performance. Are there any comparison between these techniques available, or is there a definition of the best practice? So obviously, there have been debates going on for a long time between, say, protocols like SOAP and REST. Major point being the performance, right? SOAP envelope has a lot of data, hence transmitting to and from the network is going to increase some overhead. As compared to a REST protocol or a JSON, JSON again is a slimmer version of protocol, right? Leave JSON, you could go for a REST protocol to generalize. But then you have to use SOAP if you are talking about interoperability, and if you want an extreme, if you want to have transaction support in your service or and security, kind of interoperability, there is no other way but to go for SOAP service. So there again, you need to weigh your non-functional requirements, whether you need to support interoperability or performance is the key factor there. From REST with SOAP comparison, yes, REST is of course more faster from a network latency point of view. Hence, when you don't need all of the rest of the interoperability or security requirements, you could go for REST.
If you have one question, what is the base of percentage calculation for non-domain requirements shown in the earlier part of presentation? So like I said, we have taken a typical sized project where you are trying to build a version 1.0 or an application. So the base could be anywhere between a project size of 40 to 50% months. So that's the kind of a base you have taken to calculate these numbers.
How to calculate resources based on number of users for a web-based calculation? Okay, I'm assuming the question is more on capacity planning, right? How do you, so there's no formula that directly gives you for this many number of users, this is the resources that you need to go for. So there is like you need to do a calculation based on which you derive it. For example, for your database, you know what kind of transactions are going to be there, what are the data that is going to be coming into the system from these users, right? So based on that, you could calculate the database volume, and from web server, it's typically the percentage of use of your application, right? So there are, you have say 20,000 users that you support, and the expected percentage of use of your system is like say 50% of the time all the users are going to be there in the system, which means 10,000 sessions are going to be supported at any point of time. So within the 10,000, say for example your concurrency based on your application could be 50% again, so which means 5,000 concurrency is what you are expecting. Or your application could be used once in a while, which means that 10% of the people are going to use the system at any point of time, which means directly from 20,000, you're just talking about 10% of it being live sessions being at any point of time. And within that, the usage itself could be 10% of concurrency. So you need to determine these percentages only based on your application type, right? How, is it a system that's going to be used throughout the day, or is it a system that people use once a morning or leisurely? So those things will determine the percentage, and from that you could work on the concurrency. And from concurrency, you could work on the data volume that your DB is expecting and the processing part that is expected on the web server, and work on the capacity. When you scale up, the application needs to be stopped? No, not actually. So, in fact, right now with techniques like cloud, you add servers like you add threads. So dynamically, okay, scale up. Okay, for scale up, yes. My answer was more for scale out. For if you are planning to scale out, you don't have to really bring down the system. You could just dynamically add using programs, and cloud gives you APIs to totally increase the number of servers and so on. From a scale up, and especially if you are having your own data center, yes, some downtime is required. What provisions are required in Microsoft Web Application Layer to use cloud environment as PaaS? Okay, so Microsoft itself has a PaaS called Azure, right? And your Microsoft Web applications are very close tied into the Microsoft PaaS Azure. You need to follow certain techniques to be able to deploy it on Azure. For example, the web application itself needs to be scalable, should be able to individually be scaled out, even to be deployed on Azure, which means that the states that we saw, right, be the session state or cache state, needs to be handled properly to be able to deploy to Azure. Your storage, right, from you would not be able to write directly to a file, instead use services from Azure in order to store to a file, like use the blob service and so on. So there are few differences, but not major. If you are on a Microsoft stack and if you want to very quickly move on to a PaaS environment and not an IaaS, Microsoft Azure is a very close choice. How the in-proc parallelism plays roles in web-based application. See, when you're dealing with web applications as well, right? For example, there might be 4 or 5 processes that you would need to finish before you get the output out, right? So in such cases, you could make call 1, call 2, call 3, call 4, all the calls parallelly, asynchronously, and once all the 4 calls come back, you could combine the result and send it. So this is a common pattern that's being used, and in fact, a lot of the web applications itself has started supporting this asynchronous kind of processing right now. So that's how an in-proc parallelism is useful. So you're spinning 4 calls, spin it off asynchronously parallelly. Once it comes in, combine it and send the output.
So I think as we are running out of time, we will close this session today, and the questions that we have not answered, we will try to answer them through an email. So we should be able to revert back to you within a day the answers. So I'll hand it over back to Mohini. Mohini? Okay, so I think with that we will close this session. Once again, thanks for joining, and we look forward to see you on the next 2 sessions as well. Thank you.
Well, thanks so much for the insightful presentation. I'm really thankful to you for conducting this webinar. It was indeed a great session. I would also like to thank all our participants for their support in making this webinar a success. The recording of this session would be available on techgeek.com by tomorrow. Thank you all. Have a great evening.